Friends, let us come to the final section of this chapter, which deals with the nature of physical laws. So we already understood that the Newton's law of gravitation, for example, is very universal in nature. It applies, the same law applies for wide variety of situations, from the terrestrial objects that we see on the earth to the celestial bodies up there in the sky. Here we will discuss some more such laws, some more such physical laws which have great applicability, which are always which are always applicable. So one of the first laws that you have already studied in various ways is the law of conservation of energy. What does it mean? What does it state? It says that in any closed system, a closed system is one in which the energy can neither enter nor it can escape. So if I have such a system, for example, if I have such a room, then the total energy in that room would always be conserved. So no matter what I do inside that room, whether I cook my food, whether I run, whatever I do, if the energy cannot escape that room or cannot enter that room, then the total energy of that room would always remain the same. It is very difficult to produce such closed systems, and that's why we always have certain loss and gain of energy. For example, you might think that your classroom is a closed system, but it's not really a closed system if you think about it. The sunlight can enter, and sunlight with it also brings the energy. Similarly, the air can really escape. There is exchange of air from the classroom to the outside world, and therefore with that air, energy comes in and goes out. So it is very, very difficult to create such closed system. But if we are able to create such a system, then we can actually demonstrate the law of conservation of energy inside that system. See, one of the examples of such closed system is the universe. The universe is the ultimate closed system because we know that energy can neither enter the universe or nor it can escape the universe. But of course, we cannot really do our experiments at that scale, at the universal scale. So for the purpose of our experimentations, we have to do certain approximations. We have to create an approximately closed system and conduct our experiments there. But nonetheless, law of conservation of energy is assumed to hold. We assume that it is always held no matter what we do. Now, one of the questions that we really would ask here is that is it always true that the total amount of energy is conserved? See, previously people used to believe in earlier days that there were two kinds of things which were conserved. One was energy and one was mass. So there were two different things. They considered mass, energy and mass to be two different things. And they thought that through any process, these two things are actually conserved individually. So energy is conserved individually, mass is conserved individually, and that is true, right? For example, if you do any chemical experiment, if you were to bring Na and Cl together, if I take 1 gram of sodium, 1 gram of chloride, then the total sodium chloride that I would get is 2 grams. That's what I would think, and that's what actually happens. So in most of our experiences that we see in everyday life, energy is conserved separately and mass is conserved separately. But in general, in physics, now we understand that these two quantities, energy and mass, are actually interchangeable. So I can go from one to the other because of the famous Einstein's equation E equal to mc square. Now with that understanding, physicists now say that in a system, the total mass energy is conserved. So they club the mass and energy together into one quantity, mass energy. Now with this, we come to the second point, which is very, very important. What about conservative forces? Now this conservation word is used two times. It is used in law of conservation of energy, and it is also used in the sense of conservative forces. So what about conservative forces? How are they related to this law of conservation of energy? So think about it, okay? There is a single thing which will clear all of this bring this relationship very, very close, and that is, if there is a conservative force, it would always be expressed. It could always be expressed. So if I am doing work either against this force or if that force is doing the work, as long as it is conservative, that work would always result in an equivalent change in potential energy. So this is the definition of a conservative force. Okay. So what does it mean? It means that, let's say I have this spring. This spring force, this particular rubber band has spring force, let's say. Okay, I am doing work against that spring force. I'm pulling the rubber band So I am doing work against that spring force, and this work done, all of it is being stored as potential energy, and therefore this is this spring force is a conservative force. So work done against the conservative force or work done by the conservative force always results in an equivalent change in potential energy. And if that thing is happening, this relationship holds true, then the force is said to be conservative. So this is the one and single definition of conservative force, which would help you decipher all kinds of forces. We'll discuss the conservative force in a separate class, and that would make it even more clear. So here I have another example. I have this pendulum. This pendulum is very famous. We will bring it in a lot of our classes to demonstrate the point. Here also we have a pendulum, and again this pendulum is an example of a conservative force. I'll tell you why. See, I start the pendulum from here, okay? So I am doing work against gravity to pull it here. This work done against the gravity in its all its entirety, this entire work done is being stored as the potential energy of this pendulum. So now when I throw it, that potential energy is released. Okay, so here I have potential energy, here I have potential energy, in the middle I have kinetic energy. But the key point is all the work done is stored in the form of potential energy. Okay, so as long as that relationship holds, the force is said to be conservative. We have some forces which are not really conservative. For example, friction. Now you would say that friction is not really, sir, a basic force. It is not even a force. We never understood it as a force. Then why do we even have it? If it's not the basic force, why do we deal with it? See, the thing is, friction, like we said, is actually accumulation. It is the accumulation of all the electromagnetic forces that I cannot really take into account when I am doing something. Like for example, when I am rubbing this match stick against this matchbox, there is lot of electromagnetic interaction happening between the atoms at the tip of this matchstick and the matchbox. There is lot of electromagnetic interaction which is happening, and because I cannot model that, see, it is a problem with my modeling. Okay, it is not that these electromagnetic forces are not conservative. They are definitely conservative, like all basic laws, all basic four forces that we have studied are actually conservative. It is not the problem of these forces, it is the problem of my understanding, because I cannot really model that interaction. I cannot really understand each and every force which is being put here. Therefore, I am not able to account for all the kinds of potential energies which are changing hands here. And because of that, my limitation of accounting, I just name this force instead of modeling all of those individually. Okay, when I rub it, instead of modeling all of those forces individually, I just said that there was a force here which I called friction. So I just simplified my work and actually created a new force, which is the force of friction, and use this to solve the problems. Okay, but think about it, friction is not really a force. It is actually the electromagnetic forces which are present at the surface of interaction which result in friction. All those electromagnetic forces are conservative, and if we can model the change in potential energies of all these atoms and molecules involved, we would be able to completely say that all the forces were conservative. We would be able to take into account all the energies, and we would just see that all the work done was converted into some kind of or other potential energy. But because we are not able to do that, we just created a force called friction, and because this friction is a result of our limitation, it is not a basic force. This friction happens to be a non-conservative force. If I do some work against friction, for example, I did work here when I lighted the matchstick, I did some work here, but it did not result in any change in potential energy. It did not increase potential energy of the matchstick. It did not result in the increase in potential energy of the matchbox. Nothing really happened. Okay, there was no change in potential energy. I was not able to express any kind of potential energy in a formula. Okay, this potential energy came from friction. So I was not able to really come up with a potential energy when I did work against the friction, and therefore friction becomes a non-conservative force. It does not result in an increase in potential energy or decrease in potential energy. So friction, that is the thing. Okay, so conservative and non-conservative forces, we will take another separate class on this, and that will again be very, very interesting, and it will come up with some more properties of these conservative forces, and those again, that again is very, very important. But at this point, I hope we understood the relationship between the potential energy and the conservative force, and that is the most important thing here. How is the conservative force? What is really conserved in a conservative force is the potential energy, and that is what we really have to understand. The second thing that we have to understand is that energy is a scalar. What does it mean by a scalar? A scalar means that I just have energy, right? So, for example, in the morning when I eat food, I just get energy. There is no direction associated with that energy. It is not that if I eat a mango, I will always walk in that direction. No, that is not the case. I just have energy. Okay, so there is no direction associated with that energy. Okay, I can go I can do whatever I want with that energy. I can just move my hands. Okay, so the thing is, energy is just a scalar. There is no direction associated with that energy. Now, there are certain quantities which really have direction, and one of the most important thing which has direction is actually momentum. So we'll now come to the next thing, which is momentum, and we'll understand what are vectors by seeing the example of this momentum. See, momentum is the quantity of motion. So this is how Newton defined it to be. Okay, it's not me, it was Newton. He just said that it is the quantity of motion, and he also said that this particular quantity of motion, not in so many words, but he also said that this particular quantity of motion is always conserved. It always remains the same from one point to the other point, as long as there is no force acting on the body. So this is the definition of Newton's second law. We already know that. But what does it mean by the quantity of motion? See, we understand the momentum to be this capital M. Okay, we can also write it as P. Momentum is equal to mass of the body into its velocity. So this is, you can think about it as a quantity which is conserved from one point to the other point, as long as that conserved means it remains the same from one point to the next point if there is no force acting on a particle, on a body. Okay, so it is just the quantity of motion. Another thing about this momentum is that if two bodies collide with each other, then this momentum can be transferred. So for example, if these two collide, then if this has momentum, this momentum would be transferred to this ball. So this momentum is something which can be transferred from one body to the next. So this is the definition of, this is how we understand the momentum. It is just something that it is something that we have created, and we know that it can be transferred from one body to another, and it is conserved as long as there is no force acting on the body. So now we understand this momentum. Now let's understand why it has direction, right? So thing is, if I am rolling the ball this way, then you know that the ball is rolling this way. It cannot really, its rolling action in this way is really different than the rolling action this way. Those two are two different actions. Those two are two different momentum. So this momentum really is a vector quantity. It is associated with the direction. And what is the direction of this vector? The direction of this vector is really the same as the direction of this velocity. Okay, and we mark it by using small arrows on top of these symbols. So momentum has the same direction as the velocity of the body, and really when I am moving in this direction is different than my momentum when I am moving in this direction. And to go, if I have to change the momentum of a body from this direction to this direction, if I really have to change that, then I have to apply some force. So these two momentums, although they might be same in magnitude, they are very different because the momentum is actually a vector quantity. Now what does it mean by conservation of momentum? I mean, momentum is a vector quantity. So what does it mean by conservation of momentum? How is it different from the conservation of energy? It is different because when we have vector quantities, it means that momentum in each and every direction is actually conserved. Okay, so that is what the difference between scalar and vector is. When I have conservation of a vector quantity, it means that that particular quantity, for example momentum, would be conserved in each and every direction. Okay, so if I have a body which is falling like this, okay, then it has two directions. One is it is going this way, and one is it is going down. So it is going this way also, and it is going down also. If this body is moving, then its momentum is conserved in both the horizontal direction as well as the vertical direction. So it is conserved in both the directions. That is the most important thing about the conservation in case of vector quantities. Okay, so with this we understood the what is conservation of momentum. Now another thing which is important here is that we have sort of the discovery of a particle, neutrino, which actually happened because of the conservation of momentum. So Pauli was conducting some experiments, and he actually postulated that there was this existence of another particle called neutrino, because they were not able to sort of when they observed the beta decay. So beta decay is a kind of nuclear reaction which happens, and when they observed the beta decay, they were not able to not able to explain where the momentum is going. Okay, so there was some momentum loss in that beta decay. So Pauli actually postulated that there must be some other particle which is being emitted, which is as yet undiscovered, which must be carrying the rest of the momentum. Okay, and that is how the discovery of neutrino actually happened. So these conservation laws are important because they are so universal. The people or the scientists just assume that they are true, and then they postulate their theories that, oh, there must be something missing here, because conservation of momentum can really not be violated, so there must be some other particle. Okay, so think about it this way, that they are so universal that Pauli created another particle postulated another particle based on this law. Similar to what we have in the case of linear momentum. Okay, so this is known as linear momentum, which means that it is going in a line. Similar to this, a quantity analogous to this is in the case of rotational motion. So rotational motion means that when the body is actually rotating. So if I have this ball and if it is rotating like this, okay, if it is rotating, then I have a something else, a corresponding quantity, which is known as angular momentum. Okay, so angular momentum is the analogous to the linear momentum. Okay, so if it's rolling this way, then I have linear momentum. If it is rotating this way, then I really have angular momentum. And again, this angular momentum is actually conserved. Now we understood that, okay, these are three important conservation principles: conservation of linear momentum, conservation of angular momentum, conservation of energy, and we will be using it all throughout our book. We also need to understand, why do these things actually hold? Why is it that? Why is the energy really conserved? Now, why is that the case? Maybe it's not conserved. Maybe there was loss of energy all the time. Maybe that could have happened, but it does not happen. So what actually causes these things to be conserved? So we will understand it, why the things actually are conserved. Why is momentum actually conserved? By using a very, very simple example. Okay, so that will give you an idea. See, the actual physics behind this is given by Lagrange. Okay, so Lagrange mechanics is another kind of mechanics similar to Newtonian mechanics that we will study, but because we don't really have to study Lagrange mechanics, so we will not go there deeply. Okay, to understand why is it that these quantities are conserved. We can really explain it there mathematically. We can really explain it by using the Lagrange mechanics, but we will not going to do that. Okay, and we also are not going to study the Noether's theorem. So Noether's theorem actually again explains why these quantities are conserved, but we are not going to study that either. So we will get some intuitive idea of why are some of these quantities conserved. So it is said, okay, just assume this, that the momentum is conserved because space is homogeneous. Okay, what does it mean by space being homogeneous? Now think about it this way. I have an inclined plane here. This is really an inclined plane. Okay, and if I remove this inclined plane, this is really a flat surface. Okay, so this is really a flat surface. Now, if I roll the ball on this flat surface, okay, if I start with certain momentum, this ball starts with certain momentum, then you will say that the momentum here, okay, we are assuming that there is no force now. Momentum here, the momentum here, momentum here, momentum here, at all these points would really remain the same. That's what you would say, because the surface is flat, I am not really losing any energy, so there is no reason for the velocity to change, and hence the momentum will not really change. So this, because of this homogeneity of surface, because the space is homogeneous, it is really the same everywhere, this momentum is actually conserved. So conservation of momentum happens because of the symmetry in nature, and that particular symmetry is the homogeneity of space. So homogeneity of space results in the conservation of momentum. And now we will just create a space. Okay, this is, just assume that if our space was not homogeneous, it was really like this inclined plane. Now if I push the ball, okay, my momentum actually decreases as I go from one point to the other point to the third point. And if our space was not really homogeneous, it was like this inclined plane where I was losing energy all the time, then my momentum would not really be converged. But because space is homogeneous, there is such a symmetry called homogeneity of space, my momentum is actually conserved. So similar to this, we have other symmetries in nature. For example, symmetry in time. So time 1 second before this second and the next second are really the same. They are one and the same. And therefore, this symmetry in time results in conservation of energy. If time was not really symmetrical, if this moment was different, if something really changed, okay, from this moment to this moment, spontaneously, automatically things were changing, then my energy would not really be conserved. But because time is really, translation in time is symmetric, it results in conservation of energy. Okay, so this is conservation of space. And the last thing is conservation of angular momentum. It results because all the directions are really the same. So if I conduct my experiment really this way, or I conduct my experiment this way or this way, no matter which direction I am conducting my experiment, the results would really be same. And this is known as isotropy. So isotropy is the property of the space that all directions are really the same. And because of this particular symmetry, isotropy, it results in the angular momentum. Okay, so think about it this way. All the symmetries in the nature result in one conservation law. So if there is a symmetry, there will be a corresponding conservation law. And this is actually the Noether's theorem. Okay, so you can call it Noether's, you can call it Noether's theorem. Okay, so this is the Noether's theorem, but we will not go into very much detail about this. See, the very last thing that we are going to discuss is actually the why is mathematics so important? See, we studied so much in this class, but we really didn't write any equations to see that. Okay, so to prove our things, to really express our things. Okay, but if there was an equation, for example, if I wrote the potential energy, okay, PE is due to the gravitational field is mgh. If I was able to express my thought about potential energy in the form of a mathematical equation, then it would make this particular law very much succinct. It would make this law very small, very sort of brief. I can express a lot of things in this equation. And secondly, if I have this equation, I can use it with other equations to derive even more powerful laws. So for some reason, our physical world is expressible, very much expressible in terms of these simple equations. And because the physical world is expressible in terms of equation, we should take this to our advantage, and physicists actually take this to their advantage, and they use lot of mathematics together with physics, and it makes mathematics a very powerful tool to derive even more sophisticated physics, even more laws, even more theorems. So if we can derive something using mathematics, we believe that that particular thing would actually hold, that particular physics law would actually hold. And then there are experimental physicists will go along and run along basically that mathematics. If they go along with that mathematics and try to prove that mathematical expression using their experiments. So that is why we will be using lot of maths in the case with this particular physics course. Okay, and one of the things to note here is that although differential calculus, okay, so that is the di by dt, you might have seen this sign, okay, so dv by dt, okay, this will be introduced only in the 12th class. But if you are a student of JEE, if you want to clear JEE, if you are pursuing that, then there is a separate course on DoorstepTutor in which we will be discussing all of this mechanics using the differential calculus, and that will make it even more easier for you to solve the problems. Of course, here on YouTube we will not be doing that. We will be sticking to normal formula. We will not be using the differential calculus to solve the problems. Hopefully we understood the chapter 11 very well. Thank you.